one of the more interesting things about calculus is that, or with the integral in calculus, is that we can think of that integral representing area, but what we're really doing is kind of accumulating a total amount of change. And the reason why areas can be seen as problematic is that if I go negative in an area, what does that mean? What does a negative area mean? So we want to come up with a more generalized way to represent that concept. So what we're going to do is we're going to revisit some of what we've already discussed. If we have this big F of x, and we know it's an antiderivative for little f, then the fundamental theorem of calculus guarantees that that integral of little f dx from a to b is the difference in big F at b minus big F at a. And we also know that by the definition of an antiderivative, f prime of x is equal to f of x, or big F prime is equal to little f. So if we take this formula and this relationship, then we can replace little f with big F prime. So that's kind of interesting. Now I have something that's represented only in terms of big F's. So the integral of big F prime of x dx from a to b is equal to big F at b minus big F at a. Now, if you think about what big F at b, if I have some function, don't worry about the fact that it's big F, little f, whatever, and I have a function at one value, and let's say it's an endpoint b minus the function value at an endpoint a, that's just the difference, that's the change from a to b. That's the total change that it's gone through. It doesn't, it might have gone up and then come back down, up and, or come up like this, or it might have gone straight line. But the idea is that the total change is just the ending point minus the starting point. Why is that important? Well, this f prime is the rate of change. So what that means is that if I take the rate of change and I follow it all the way along a to b, just, the ups and the downs, if I just take that rate of change, then what I end up with is the total change, or what we might call the net change. So what is that? How does that relate to our normal integrals? Well, what it says is that if I'm taking the integral of little f, what I'm really saying is that this is just representing the total change of its antiderivative over time. And this can seem a little bit nebulous, but the idea here is probably the easiest way to think about it is in terms of velocity and position, right? If I'm traveling somewhere at 60 miles per hour and I travel for 1 hour, I've had a change of 60 miles. However, what if I travel at 60 miles an hour for 1 hour and then I actually have to turn around and come back halfway, and again, let's say I'm going 60 miles an hour, I have to come back halfway, and then for like a half hour, and then for another hour I travel at 60. So I go 60 miles, I come back 30, and then I add another 60. So my total change was 90 miles. And I could do that by following positive, negative, positive over the entire integral, or over the entire interval. So what we do is we can say, okay, well, if I have a velocity, that's the rate of change of the position, right? That's just telling you how quickly your position is changing. We can find the net change in position by evaluating this integral. So if I know what my velocity is, I can find what has happened to my position by integrating. This is incredibly powerful because as you study more and move on into things like multivariable calculus, what you can do is you can represent the velocity not only as some sort of function of one variable, you can represent it as like a vector. So if you know the speed of something, or rather it's velocity, but a lot of times it's speed and an orientation. If you know the speed and an orientation, you can use the integral to find where you predict where you're going to go. So in a lot of computer simulations, this is exactly what happens. You have some information about the state of a model. You know that it has a certain velocity, and so then you can walk forward in time and take the position and move it to where it's going to be when it updates. Again, computer simulations are all over this. It's a very, very important concept in how we apply sort of like real world math. So again, if we take the change in position, which is the velocity, we integrate it over time, that gets us the total change in position. So an example of this would be, okay, I want to follow the displacement of a particle. So displacement is also that net change, because that's just how far it's displaced from where it was. So if it's moving along a line, so in this case we have just one dimension, and the velocity is modeled by this t cubed negative 10t squared 29t minus 20. So if the velocity models that on the interval 1 to 5, we can say, okay, that's kind of going wild, right? Because it's up and down or whatever. I don't care about all that. All I care about is where did it get to from where it's from. So what I do is I take the integral here. I do my starting time and my ending time. I take the velocity function, I plug it in, I find its antiderivative. So I find a general antiderivative for f, or rather a specific one here, and then I evaluate it at the endpoints. And when I plug in this, I didn't evaluate it here because of board space, but I'm sure you can do it. You end up with 32 thirds. What that tells me is wherever it was at time equals 1, and we're not given that, we know that in the next 4 seconds it will be 32 thirds whatever units it was, right? Because we weren't given units. It'll be 32 thirds units in front of where it is now. But that doesn't tell you the whole story. That doesn't tell you where it went. So I might have said, okay, it goes 32 thirds, but did it go straight there? Did it go back and forth and back and forth and back and forth and then finally end up there? Did it go further and then come back to where it is? We don't know that. So the only way to get extra information is to find what's called the total distance traveled. And the way you want to do that is instead of integrating the rate of change just generally, you integrate the absolute value. What that means is that you treat any change in position as positive, whether you're going this way or that way. Think of it sort of like when cars are doing the Daytona 500, for instance. If you were just evaluating the displacement at the end of the race is basically zero. You go around and around and around and around, and you start where you end where you started. So from a displacement standpoint, you haven't really traveled anywhere. So it's like, well, why did I use all that gas if I didn't go anywhere? But if you discuss the total distance traveled, you can see that you're going around and around and around and around. You're just going positive and then negative, and then positive and then negative, and positive and negative, and it's all canceling out. This helps you keep track of the total change that has happened.